Hello and welcome back to Ultrasound Physics. So today we're going to talk about transducer and beam. And as always, remember your actual lecture material should have already been covered. This is just going to be very brief summaries to just make sure we address the learning outcomes and also to go through a few sample problems. Okay, so by the end of this, you need to know the equations for the near field and the far field component of that wave envelope. And not only do you need to know the equations, but you need to know each factor of the equation and how that's going to affect the near field or the far field, the distance, the beam divergence, etc. Secondly, we've always now thought of ultrasound as this single array that just comes out, very simple to explain, so we can look at the wave as a single wave coming out and it makes sense. But in reality, there's a lot of different types of transducers and they're going to have multiple arrays. So we're going to look at the different types of transducers and how they affect that final wave envelope. Okay, so far in this course, we've assumed a single transducer element generating multiple sound waves. And we do this because it's going to be mathematically simple to explain and it gets the point across. Okay, so what happens here is once we create the sound waves at this transducer surface, they constructively and destructively interfere. Now in the very near zone or in the region very close to the transducer, what that ends up actually doing very close to it is it starts to collimate the beam tightly and converges the beam towards a specific point at a distance. This point we'll call our focal point. And remember, this is a non-focused ultrasound beam. So we haven't applied a lens to it, we haven't changed electronics to do electronic focusing, nothing. It's just an unfocused ultrasound beam. So this zone here, because of those interference patterns, we get this very tightly collimated beam. We call this the Fresnel zone or the near field. Now, once we get to the focal point, we get what we kind of expect to actually have happened around here. And that is we get a beam divergence in this region here. And this zone is called the Fraunhofer region or the far field. Now in this zone here, the intensity of the ultrasound beam reduces with distance, as we would expect. Here, there's a lot of things happening with those constructive and destructive interference, so we get a lot of maximum and minimums in terms of the beam intensity within this region. Okay, so we'll talk about each zone in more detail in the next slides. Okay, so in the near field, we'll draw our transducer again. So what affects this near field? Okay, so we need to know the length and how long this near field will go for. Okay, so to do that, we have a specific equation that describes that. So the near field length is given by the diameter squared over 4 lambda. So what that means is the actual diameter here of the transducer element, the size, the physical size of the transducer element, and the wavelength will tell us how long this near field zone actually is. Okay, so as we increase our wavelength, we actually make this zone shorter. So that means for a higher frequency and a shorter wavelength, we're going to have a longer near field zone. Okay, so we know now as well that anytime we have wavelength, we can also represent that in terms of frequency as well. So that will be d squared multiplied by the frequency over 4 multiplied by the speed of sound in the material, or 1.544. Okay, so again, what gives us the distance in terms of the near field length, and this is important to know, is the diameter of the element the wavelength or the frequency, and we need to know that if we increase the frequency, we get a longer length, or we shorten the wavelength, or if we increase the wavelengths or shorten or decrease the frequency, we get a shorter near field zone. Okay, and this is all up to this. This is the distance from the transducer to the focal point. So remember, unlike focused beams where you have a focal zone, here we're talking about an unfocused beam where all we have is a focal point, and from here it actually starts to diverge. Okay, so if we draw our transducer again, we have our near field, we have our focal point, and we have our, now we're talking about the far field or the Fraunhofer zone. So here, to describe this zone here, we're not talking about a length anymore because now it's just divergent until the beam intensity drops all the way down to 0. Okay, so it's just going to keep divergent outwards. What we want to describe is actually from the point or from a straight line from the norm, what is this divergence? Okay, so if we draw straight lines from our transducer element, how far is it diverging? So we want to figure out this angle here. And to do that, we just go sine theta equals 1.22 multiplied by lambda on d. So what we see here straight away again is that the diameter of the transducer element tells us how much divergence we're going to get, as does the wavelength. So it's the same thing again in the near zone where those two values told us what's going to happen here. It's the same thing happening here as well. So it's all related to the wavelength or the frequency, because we know frequency and wavelengths are related, and the diameter. So because diameter here is on the bottom, that means if we have a larger transducer element, we get a smaller divergence. Okay, because this value is going to make it smaller here. As this increases, this will get less. And if we have a larger wavelength, okay, so we're up top here, if we have a larger wavelength, we're going to get a bigger divergence. Okay, so that means high frequency, large diameter, less divergence. Low frequency, small diameter, more divergence. Okay, so, and this is how we figure it out. Sine theta equals 1.22 wavelengths over diameter. Okay, so in B mode imaging, like we said before, it's basically a number of A mode lines that come back, reflected into some sort of amplitude, and that amplitude is going to give us a conversion to a grayscale based on the depth of the reflector and the strength of that reflector, and that's going to draw an image here. So the first thing we're going to look at is a linear array. Now, what a linear array is something that is spaced linearly, and it is fired, the piezoelectric elements are fired or grouped together and then fired in a sequence. So we have here a sequential progress of those lines. So we shoot one line, wait for the reflection, we go back, and then we shoot line number 2, wait for reflection, we go back, shoot line number 3, wait for reflection, and so on and so forth. And we can see that happening down here. Okay, so we kind of move across the image, creating this image, one at a time. One line at a time. So typically in a linear array, we have around 250 to 500 elements, and we group them together in, say, 20 elements at a time. This gives us good enough power to go through the patient and get a good signal to create the image. But what it does also do is when we group elements together, we kind of lose lateral resolutions, because when we have 20 elements together, we've increased our width here, and that width means we won't be able to resolve anything that is smaller than this, because we'll pick up anything that's smaller as a specific signal if they're very close spaced together. But it's good because it gives us a focus. It's easy. It's just one at a time, and we create this sort of image. Now, the problem here is when we create one image, one line, it takes some sort of time value to go down a specific depth. Say it's down 10 centimeters. It takes a specific amount of time to travel that distance, and then a specific amount of time to travel back, and that will be our pulse. Then we go to the second one, and we do that, and we wait. So there's a time delay between each specific one because we have to wait till one line finishes before we start the next line. So what we end up having here is a or a limitation based on the frame rate we want to see. And that means we're going to have limited temporal resolution here. So if this is a moving image, this is not going to be great because by the time we scan our 10th line, this may have already moved, and then the 10th line will be different to what the image looked like in the first line. So we're going to have a limitation here set by our frame rate, and we're going to work through a good example here in this lecture about how we work out what the frame rate actually is. And typically in this sort of setup, we want a frame rate that's greater than 50 Hertz, because under 50 Hertz, it doesn't quite look like a movie for us, like a continuous movie. It looks like a bunch of images stuck together. Whereas above 50 Hertz, our eyes will think it's just a continuous movie. So if we can make sure that this is above 50 Hertz, we can image something here. So the way we do that is we can only image things that are shallow. So this is very good for shallow imaging. Now, same setup as before with linear arrays where we have a sequence of images. But what we can do here is we create a curvature. So we can call this a convex array or a curved linear array or a curved linear array. And these are similar because we group our piezoelectric elements into groups of 10, 20, whatever it is that we choose, and we emit them into the patient. And this change here will change our focus. So this will give us a different focus, and will also give us a different field of view. So we can see here now our field of view is no longer rectangular, it is trapezoidal. So this increases our field of view at a depth, which is good for specific imaging. But the problem with this is you can see here, when we go down to a specific depth, we start losing that lateral resolution. So the density here at the lower depth is going to be lower. So this is good imaging for specific reasons, and it gives us a larger field of view and gives us a fixed focus here. But we also lose that lateral resolution down the bottom. Now, a phased array transducer is going to act differently than what we saw before with that sequential moving of lines. So a phased array transducer, we can fit all our elements into this very small transducer, typically centimeters long, and it will have roughly 64 to 128 elements, and we fire off all the elements at the same time. Now, the key here is we set at the same time, but we do also add a little bit of time delay between each element firing. But it's not wait until the whole thing comes back and go again. This is literally firing them all with some delays, because the delays help us steer and focus this beam. And we'll learn a lot more about that in the steering and focusing lecture. But for now, just assume they're all getting fired off at the same time with some minor delays between each element firing. And we can then choose that delay, which will give us a different focus in the beam and a different steering. So we can actually fire it down this way, but focus the beam into this direction or into this direction without really moving this, but doing that electronically. Okay, so the advantages here is going to be a very small transducer. We can image in small spaces. We can change the focus as we move along. So if we don't like, if we need deeper focus or more shallow focus, we can electronically change that on the fly. So what we do is we just add this slight delay, but we fire them off roughly at the same time. And then when we receive them, we add a delay to the signal again as we receive it, so we can construct it in a way that will give us an image that has a specific depth of focus. Okay, so we'll work through some questions now. And this question here is a typical kind of exam question, and we're trying to cover everything we know about that near field and the far field. Okay, so we're assuming a singular circular element. So again, we're going to the basic principles of a non-focused ultrasound beam. Draw a diagram of the field components and label N, D, and theta. Okay, so first of all, let's draw the diagram. We've got a transducer element. We've got the near field, and we've got the far field. Okay, so now we want to label each part of that diagram. So D, we said, would be the diameter of the transducer. So D is this value here. Sorry about that. So this is D, the diameter of the transducer. N would be our near field length. So that's the equation we looked at before. So N is this value here. And theta, like we said, is if we took values of a straight line coming out of the transducer, the angle of divergence will be our theta value. So the near field region is a region of best lateral resolution, and that's because it's got a narrow region here. So we're going to be able to see things that are closely separated side by side. So for example, if two things are separated here side by side, they will return a single signal back. If we go here where it's more narrow, there'll be two separate signals. Okay, so what happens as the frequency increases? So we said before, when the wavelength here increases, we get a decreasing distance. So that means when we have less frequency, we get a shorter distance. So to get better lateral resolution in this sort of setup, we actually want higher frequency, shorter wavelengths. So if we increase our frequency, increase F, it increases the distance here. And we get a longer near field zone, which gives us better lateral resolution. Okay, so the near field region is the best lateral resolution. Again, what happens is the crystal diameter is made larger. So we look at it here. Diameter is on the top. That means if we increase the diameter, we increase our distance here. If we decrease our diameter, we decrease our distance. So as we increase diameter, increase D, we increase N. Okay, so to put in wavelengths as well, so that means a decreasing wavelengths will give us a better lateral resolution here. Now, finally, the self-focusing effect. So the self-focusing effect, remember we talked about this as an unfocused ultrasound beam, but it actually focuses itself because of all those constructive and destructive interference patterns that are happening here close by. We get to a point where that gives us this value here. And this is our focal point. So this focal point, we're saying that the ultrasound beam self-focuses to this point here. Okay, and at this point, we're going to have the best lateral resolution. Okay, so this here is a great exam style question because it has multiple parts to it and it uses everything you know about ultrasound, but also first principles for physics. So let's draw a diagram to make it easier for ourselves. So that's 7.7 centimeters. We have a reflector and it goes down 7.7 centimeters, and the key here is it goes up again 7.7 centimeters. So you have to know that because it's not just a distance down. We also wait for it to receive it. So the time in microseconds for the pressure wave to be emitted and then detected. Okay, so here it's going to go 7.7 centimeters down and 7.7 centimeters up. So D equals 2 by 7.7 centimeters. We should put that in meters because we know the speed of sound in meters. So it'll be 2 by 0.077, which equals 0.1540. Now we know from, again, first principles that time equals distance over speed, or speed equals distance over time. So we just work that equation around. Now that, if we plug in everything we know, that's going to be 0.1540 over 1540 meters per second, and here's meters. Okay, so we can cancel these out and we'll have T equals 0.1540. If we put that into into the same sort of units so we can cancel things out and make it simpler for ourselves, we'll have 0.1540 and we move the 0, 1, 2, 3, 4, so that's times 10 to the 4, and we've got seconds left over, so seconds to the -1. Okay, so we can cancel these out, that gives us 1. We can flip this to the top, times 10 to the -4, and seconds to the -1. seconds to the positive 1. So now we have a value of 1 times 10 to the negative 4 seconds. If we want to get that to microseconds, we just go 10 to the negative 6. So that will be 100 microseconds. Okay, so from the previous question, we had t equals 100 microseconds or 1 times 10 to the negative 4 seconds. Okay, so we'll work in 1 by 10 to the negative 4 seconds just to make this easier for ourselves. So remember we said each line takes this much time to go down, reflect off 7.7 centimeters and come back up. Now we want to see how long it's going to take to create 100 lines. Okay, so this is our pulse repetition period per line. What is the total time it's going to take for 100 scan lines? Okay, so all we have to do here is actually multiply it by 100. So t equals 1 by 10 to the negative 4 multiplied by 100. Again, if you want to put in scientific notations to make things easier for you, but you can see here what's going to happen. But if you want to put in scientific notation, what you can do is just say 1 by 10 to the negative 4 multiplied by 1 by 10 to the 2, which is going to give you 1 by 10 to the negative 2. So that's how much time it's going to create one complete frame consisting of 100 scan lines. Okay, so literally all we did was just take the time it took for one line. How many lines are there? There's 100, so just multiply the time it took for one line by 100. And that gave us 1 by 10 to the negative 2. So this gives us how long it's going to take to create the frame. Now we want to know what's the frame rate. So this is the time it takes to create one frame, but we want to know how many frames per second. So literally it's just going to be, so the time is 1 by 10 to the negative 2 seconds. Frame rate is just going to be the inverse of that. So it's just a rate, which means how many per second. So it'll be 1 over 1 by 10 to the negative 2, which will give us a frame rate of, remember, if it's 1 over something, we just make this a negative into a positive. So it'll be 1 by 10 to the 2 seconds over 1, because here's seconds at the bottom. So we flip the positive into negative, or we can say it's 100, and we know seconds to the negative 1 or rate is going to be given in hertz. So it's 100 hertz. That's our frame rate, and that's the answer to question 3. Okay, so like we said in the lecture, so 100 hertz is good because the human eye, if it sees something greater than 50 hertz, it will think it's a movie, and we won't see the jittering or the lag as we do the image. It won't look like a bunch of photos just stuck together. It will look like a continuous flowing image if it's greater than 50 hertz. So this is greater than 50 hertz. Okay, we've got here a very easy question that you should just be able to see from your lecture. Okay, so curved array, like we said, it's going to have a curved transducer, and the envelope, what's going to look like is one line at a time. Okay, so we have a smaller distance up here and a larger distance at the bottom. It will give us a field of view that looks like a trapezoid. And we're going to lose that density at the bottom of the image because we're going to spread out further from the thing. A linear array is the same sort of thing, one line at a time, but linear with the lines parallel to each other. Okay, and we're going to get a rectangular field. A phased array is going to be a small detector. We're going to have a delay, a time delay here in the detector electronically, and we're going to fire a bunch of signals all at the same time, and we're going to steer them in a specific direction to give us a focus at a specific depth inside the field of view. Okay, so I would refer back to our lectures for this because there's obviously much neater diagrams and you'll be able to draw them from there. Okay, so the last question here as a bonus question, this is the one you're meant to do on your own. So how does changing the number of scan lines affect the image quality and frame rate? So if we say there's 100 lines to create the image, by coupling 20 elements at a time, we create a line that's going to be of a thickness of how many elements we couple, or how many elements we fire off together at the same time. Now, if we reduce the number of scan lines, what we end up doing is we group more elements together. So this line here will actually be thicker. Okay, let's just say we halved it. We're going to group more elements together, and this line here will be thicker, which means we actually reduce our resolution, because now we have a wide beam. So if there's 2 points that are separated, outside the thing, we'll see them as separate signals. But there's 2 points at the exact same distance inside the field of view, or sorry, inside the ultrasound beam. We're going to return back a signal, which is going to show us a poorer lateral resolution, where we would have actually imaged those as separate ones if the scan lines were smaller. But what we're going to get here is a higher frame rate, because we're going to be able to create the image quicker, because we're just firing 40 elements at the same time, coming back, firing another 40, and we're going to be able to finish this entire scan line very quickly.